Hello everyone, my name is Bart Schenck and I am an application engineer for the Additive Corporation. Thank you for joining us today for our presentation about how the world of product design is evolving in order to keep up with the latest technology in additive manufacturing. My hope is, by the end of this session, you will have a solid understanding of how the latest design tools can be leveraged by any company who is looking to or already has invested into additive initiatives. Today, we will be using an example part from a real bicycle company that was used as a successful proof of concept for their use of additive manufacturing and generative design. But before that, let's start with some basics about the world of additive. Here is the general flow of today's session. We will start by outlining some common business goals for those who are using additive manufacturing. The subsequent material is all about how additive is changing the world of design with new tools and processes. Finally, we will show you how we can optimize and make our example part. Why is the future of additive now? To better understand why, we need to understand some of the goals of companies who are implementing additive strategies within their businesses. In my experience, there are three main goals that these companies have in common. They are part lightweighting and topology optimization to print parts faster with less cost, automated production to simply set things up and scale up as you need to go, and flexible manufacturing, being able to offer a wide variety of products with quick turnaround time. The most common goal is lightweighting. Companies need their parts that are lighter but are just as strong as the legacy components. The two other business drivers are related to the automation potential and flexibility of additive. This is true especially when compared to traditional subtractive methods. Now let's see how this can be achieved. In today's session, we will focus primarily on part and product lightweighting and optimization. As you know, many industries, such as aerospace and transportation, rely on weight reduction to reduce their products' cost to own and operate. Please keep in mind that this is just one of many benefits of this new design approach. In recent years, software vendors have been developing specific tools to enable designers to create new versions of legacy parts. The new designs are fully validated with their specific load conditions, and an organic and optimized shape can easily be achieved. This is accomplished by incorporating FEA and topology optimization into a predefined design workflow. The images along the bottom of the screen are examples of how designers can go from simple space reservations to unique organic design variants. With traditional subtractive methods, these unique topologies would be very difficult to manufacture, or potentially impossible. However, with today's 3D printing technology, these parts can be used as anything from functional prototypes to full-blown production parts. As a result of the need for design optimization, a new design discipline has emerged to lead the way for additive manufacturing processes. This process is called function-driven generative design. It is truly a new way to design. The naming is appropriate as the general idea revolves around using a part's functional specifications and its design space reservation to help determine the optimal part. Some of the generative design software tools can even propose new shapes based on your desired manufacturing process. This can include milling, casting, or 3D printing. While there are multiple tools that exist in this discipline, for today's presentation, we will be using CATIA 3D Experience on-cloud solution. The 3D Experience role that will be used is called Function-Driven Generative Designer. We will soon see how solutions like CATIA on the 3D Experience platform can combine solid modeling, FEA, and surface modeling within a single environment to allow designers to become optimization experts. In the design world of yesterday, optimizing a part's topology or overall shape while maintaining its strength and functionality was a very linear process. As you can see in this diagram, there are a minimum of 3 different people involved in multiple tasks. Data must be passed back and forth for each design iteration. This consumes a lot of precious time. Also, everyone stays in their own proverbial silo and only deals with their dataset within their own specific software. Now, each of these steps can be done by one person with a new generative design workflow. Here is the workflow for the new discipline of generative design. As you can see, this process starts and ends with a single designer. Starting in the top left, you can see how the legacy part is made into a design space model, meshed for analysis, and then optimized. The designer enters the load specifications through an intuitive workflow assistant to make sure all relevant information is present. The user can also define how many variants they want to generate and use multiple load cases in their optimization. Robust comparison tools then allow the user to review their design options in a dedicated tool called Trade-off Study. Once the optimized part is chosen, detailed surface modeling and refinements can be made, and the final part is ready to be printed. Now we will begin looking at our example part for optimization. As mentioned before, this is a suspension rocker link from a real bicycle OEM. The image on the left is the traditional casted part. The company has identified this part as unusually expensive to produce due to its unique shape. Therefore, we were asked to help this company explore whether parts like this could be optimized and additively produced. The next video will show the steps taken in order to optimize this part's topology and get it ready to print. Here is the legacy data that we are working with. On the right is the legacy part by itself, and the left is the part in its assembly context. Let's get the optimization started. We will use the assembly context to determine the design space or available volume that can be used. The shape will be the starting point of the generative design process. Within the generative design application, a design study is started. This brings up the setup assistant, which will guide the designer through some of the analysis setup portions of the design process. As you can see, there are just a handful of guided steps that are performed in order to get an optimized model. From initial model configuration, constraints, and load cases, to manufacturing constraints and thermal conditions. These new applications have clearly been tailored for the additive industry. Next, we begin to define the functional specifications of the part. The guided workflow assistant allows the designer to easily create and modify connections, constraints, and virtual parts within their optimization analysis case. As you can see, the load case conditions are incorporated directly into the model. By placing these loads and forces onto the design space model, we are prepping the generative design engine to compute multiple variants that will serve the same functional purpose. Here we see the creation of multiple load cases, building even more intelligence into this model. With our load cases set, we are now ready to mesh the part and run our initial part analysis. The mesh parameters are also controlled in this step. They can be automatically created, or you can key in your own values. A 3D mesh is generated within the design interface, and we are getting closer to being able to run our optimization. After a quick verification by the setup assistant, we are ready to run the first analysis case. This initial analysis run will be the baseline for the topology optimization in the next step. Keep in mind, these analysis calculations can be run locally or on the cloud. As soon as the calculation is complete, the results are ready to be displayed. The displacement and deformation models are the drivers that help combine FEA and iterative topology optimization. With the initial analysis run completed, we are now ready to run our first optimization case. Before we run the optimization, we must first define the functional regions of the part. In other words, the areas of the part that cannot change their overall shape. We then partition the design space so that those functional regions remain intact during our next analysis. As we prepare to launch the topology optimization job, the user can define how many iterations will be run. Of course, the best results come from more iterations. However, please keep in mind that more iterations takes more time. The user can also define their target mass, which is the desired percentage of the original part's material that they believe is ideal. In this case, we're using 75%. The Run button is clicked, desired iteration count is defined, and the job is ready to begin. On average, running between 50 and 100 iterations takes around 15 minutes or so on a model like this one. Once the job has run, a convergence model can be displayed to easily visualize what design variants you have to work with. CATIA can then automatically generate a solid model that best approximates the shape that you choose. Here we can see such a model. Once the user gets to this point, it is time to use the best-in-class surface reconstruction tools in the industry. Here we can see the user creating strips using the Imagine and Shape engine that CATIA surfacing is based on. In this accelerated view, you can see how much control the designer has in order to best match the design variant that was chosen from the generative design workbench. Another key advantage here is the direct surface modeling techniques that can be used with a subdivision surface, like this one. As we jump ahead, you can see the one-click process for taking a subdivision surface and creating smooth and printable geometry. This process can be repeated as needed until the part has been fully optimized and ready to be sent to your printing software. Here is the part ready to print, and we are ready to go. Next, we will be showing you how this part is printed, cured, and inspected on the MarkedForge Metal X printer. Thank you all for your time, and have a wonderful day.